Good afternoon. This is Jennifer Beliveau, Sales Representative from Applied Math Modeling and today's moderator. Thank you for joining us online today. We're excited to share with you another great case study using CoolSim software optimizing the energy envelope in the data center. With me online today is Paul Bemis and Liz Marshall, Applied Math Modeling's President and CEO and Director of Technical Services, and Magnus, President of Ansys Incorporated. Before we get started, we'd like to inform you that we will have a question and answer session at the end of today's presentation. You can enter your question in the question panel located on the right-hand side of your screen. If you're having technical difficulties, please click on the raised hand icon and we'll respond to you through the chat window. Let's get started. Paul?
Thank you, Jennifer, and welcome everyone to the broadcast today. We're going to be taking a look at a couple different data centers today. This is part of some work that I have recently done, and I thought it would be a good opportunity to show you how we're doing it, what we're doing, what the logic is behind it. And it's all in the area of optimizing the energy envelope in a data center. So let me first start off with a quick overview of who we are. Applied Math Modeling is responsible for the development, sales, and support of the CoolSim application. We are a partner of the Ansys Corporation. We did spin out of that corporation now for, I guess, 5 years ago now. We build the tool and are focused on delivering cost-effective engineering simulation using a SaaS model of delivery, software as a service. So unlike traditional approaches where you have the solver sitting next to you and running on your local machine, here we are using the power of the cloud computing to be able to do the heavy lifting of CFD, which includes, of course, the meshing, the solving itself, and then the post-processing. We are experts in the field of CFD. We have been around it a long time. Liz Marshall here is with me today and has been in this field for some time and has extensive experience in modeling physical phenomena using the fluent Ansys software. And we are here, of course, to help you with any kind of situations you run into. I also have Magnus with us today, and Magnus is with the Ansys Corporation. Magnus, if you'd like to do a quick introduction, that would be great.
Yes, thank you, Paul. My name is Magnus from Ansys Incorporated. We're helping end users generally with energy and thermal management in data centers. We have done a lot of CFD simulations throughout the years, and right now we're heading up the U.S. Department of Energy's Data Center Energy Practitioner Program. That is an effort to educate those individuals who go into data centers and do energy assessments.
Thank you, Magnus. Now, what we're going to do today in this webinar is we're going to build a model of an existing data center, actually two of them. I'm going to do two today. We're going to validate the model against measured data. We're going to adjust the model to improve performance, and then we're going to estimate the cost of improvements and project the ROI. The sequencing that I go through is always the same. It's always build a model, validate it, and then use that model to project what would happen under conditional change. This is what we do in CFD. We always build models and then validate. We need some way to ensure that the mathematical model that we're using represents the physical phenomena that we're trying to predict, simulate, and then use the model to push it into areas that we have yet not tried out. The first model I'm going to look at today is from a customer. They're both the same customer in this case, but what's going on here is they're a co-location provider. And what I'm finding is colo providers are becoming more sensitive to this issue of energy, of course, because they're really competing on the cost of infrastructure. That is to say that when they compete against another colo provider, if they can deliver the same amount of power to that IT server for less money than their competitor, then they have the opportunity to either deliver at a lower cost point, therefore drive their price down vis-a-vis their competitor, or at the same price point enjoy more margin and more profitability. So this provider owns several medium-sized data centers and would like to understand the issues associated with cooling efficiency. So we're going to take a look at two of them today and show you the methodology we use and show you the predictions that we've made with respect to improvement, energy improvement. The first case is quite a straightforward one. We're going to build it with the CoolSim modeling software. We're going to calculate the energy consumption. Then we're going to modify it to take a look at a variety of situations. We're going to be using some metrics here to improve the performance of it, the same metrics that, in fact, Magnus introduced me to in the DCEP training that I went to, I guess, about a year ago. We've incorporated some of those metrics into the CoolSim output software, and it generates them for you. And this is a very nice way, I think, and the reason we're working together, because this is we both believe this is a very nice way to drive the simulation. There are indices that allow you to optimize the design through an inspection of the indices. So we're then going to increase the cold air supply temperature to improve the efficiency, and then determine the optimal design. So the first case we're going to look at is a relatively modest in size, about 4,600 square feet, 2-foot supplied plenum, 3.5-foot return plenum. It's got 4 cracks in the room. The flow rate through those crack units right now, with all 4 running, 60,000 CFM. Heat removed by them, 75 kW. Total number of rack rows, 30. Total heat load for those racks, 70 kW. Therefore, the approximate amount of CFM that those racks need in order to do their cooling is just about 11,000 CFM. So we've got 11,000 CFM of requirement here, and we're currently generating 60,000 CFM of total cooling capacity. Liz, it's not unusual, is it? That
no, not at all.
And,
people are overly cautious.
Yes. And the reason that we see it is because the data centers are often built to be able to handle max load conditions. I suspect these are 10-ton units, and there's going to be 4 of them, so they're blowing about 15,000 apiece, and there's your 16,000. So it's not unusual that you have them all running. The problem is that the energy efficiency when they all run like that is awful, as you'll see. Mm-hmm. So now here what I have, I've embedded inside this PowerPoint presentation output from a CoolSim run. This is some of the new output that we're going to be featuring in our upcoming release version 4. And we've added a few things here that I think are worth noting. Liz has worked pretty heavily on this as well in preparing this this new output format. So we'll take a walk through it, Liz, and you can comment as appropriate. Mm-hmm. Now, first of all, this is a co-location environment, and so you see the use of cages. Now, I've used Baffles to represent the cages. They are 95% open, so they don't offer much resistance. But you can see that the way they work in a colo, of course, is that customers have these rooms, so you buy essentially a room with square footage in it, and you put your servers in the racks. You own the servers in the racks. You will also notice, however, that some rooms have nothing in them at all, like this one right here is empty. It hasn't. So the point is that you buy the cooling capacity, in this case we've got 4 cooling units, to handle worst load, max load conditions, and you slowly, over time, come up to that load condition. And what you need to try to do is scale your cooling to match your IT load. Now that's the trick, is try to get the cooling to be consistent in terms of its capacity with the total IT load. Now at first thought you say, well, I've got maybe 20 tons of cooling in the room, that should be sufficient. I don't need it all, so it won't reject it all, and that is true. It rejects only what it needs. But what happens is the fans are running, in this case, full tilt. These are DX-based units, so they run with their fans fully on, which means you have a tremendous amount of airflow going on that's not needed and a wasted energy. So let's take a look. Over here on the left are a bunch of hyperlinks that show the various condition of this room. And we'll start off with the summary report, and I'll show you a couple of new features we have in here. The summary report here shows the overall data center, its summary on its performance, its cooling capacity, and so forth are all summarized here. Highest temperature in the room in this case, 79 degrees, 62 degree Fahrenheit, is the highest rack inlet. Highest temperature in the room, 79 degrees. Now, one of the things we've added here, and I'm going to review these metrics in a moment, so you can bear with me until we get there. But what we have here is a data center energy report. We build it right into the summary report now. And it lists the coefficient of performance. It lists the PUE, DCIE, RTI, RCI high and low, total facility power, and annual cost. So we're projecting annual cost here based on a set of metrics that you put in through an energy panel on the front of the simulation interface before you make a run. And the numbers here are quite poor. Coefficient of performance, remember, is the amount of heat rejected by the data center compared to the amount of work required to reject it. That number should be, for DX-based units, at least 3, chilled water-based systems 4. If you're using economizers, we've seen it much larger than that. 5, 6, up to 10, depending on where you are in the world. You see this one's is operating at 1.9. PUE we'll discuss in a moment. I'll go over each one of these for you, DCIE. But let's just leave for now the fact that we'll come back to these metrics, but let's just leave for now the fact that this one is running quite poorly. And it is running poorly because it has way too much airflow. Now here, Magnus, the RTI on this particular report right now is showing 18%.
Yeah, the first to understand is what is the return temperature index, RTI? Mm-hmm. Well, it's really the ratio between the volume of air going through the electronic equipment compared to the volume going through the air handler unit. So first thing we can notice is that when the RTI is 100%, we have a balance, so we have as much airflow coming out from the track units as we have going through the electronic equipment. You might consider that to be like a target number. If the RTI sinks below 100%, and in your case you had, what was the number you had, Paul?
18%.
18%. That means that since we have between the volume through the equipment by the volume through the air handler, we have a lot of going through the air handlers that are not really used by the electronic equipment. So we're creating bypass air. And bypass air has two negative effects. One is that we need to all that air around in the space, and that requires energy. And also, we're depressing the return temperature going back to the track unit, and that means that it's not going to be as efficient.
That's correct. So what it does, it means the cooling system is running harder than it needs to run because it's not getting good return air temperature.
So the RTI is a quick measure of, do we have net bypass air in the space? That happens when the number is below 100%, and if the number is above 100%, we have net recirculation.
Right.
And we get net recirculation when we don't have enough air coming from the air.
Yep.
Right.
So now there's a bunch of other information here, but this is to Magnus's point right here. This next little section is called the crack performance report. And here we're looking at average supply temperatures. Now the reason these average supply temperatures are 55 is based on exactly what's going on in that room. We measured the supply temperature. I had the customer measure the supply temperature, and he has it set for 55 degrees of cold air. But look at some of these return temperatures, Liz. I mean, in one case, I've got a delta of 3 degrees.
3 degrees, yeah.
3 degrees on crack number 3. Because it's blowing 15,000, it's too high. So you have a situation here that we've got way too much airflow, not enough delta T, and this crack number 3 is running way off its design center. These are designed to run at 20 degrees delta T, and I've got 3. So now we've added a couple other things here that might be of interest, and I should just explain. One of them is we've always had the rack inlet temperatures, the rack inlet contours, and these are the temperature profiles of rack inlets. They are color-based profiles or contours, and they're showing you temperature as a function of color. And they take the range of temperature that is measured in the room, the high and the low, and they spread a color spectrum out across it. You see here that there is some spectrum in the room. It's really very cold, mostly. But there is a little color spectrum in the room because you have color variation. Sometimes these are a little misleading for people because they can look like color contours and not have much of a temperature range. You really have to interpret them to understand if those racks are in or out of conformance. So we added a couple more. This is something that we talked about with Magnus, and Liz did this implementation. We have two here. One of them is called the ASHRAE recommended range. This is really a kind of a go, no-go gauge. This one is, do my racks fit within the specification recommended by the ASHRAE standard for Class I rack inlets? The range, as you can see, is 64.4 to 80.6. Anything below 64 is going to show blue, solid blue. Anything above it is going to show red. So what you see here is that this data center is way below the recommended inlet temperatures for Class I standards. It's simply too cold. Now, the allowable is a little beyond that. The allowable goes to 59 degrees, and you see there is one rack in the room way up here that is somewhere near specification. But other than that, we're way out. So the room with 4 cracks on is just way too much air and way too cold. Now, the first thing we do is validate the model. So we took this model, we validated it, and in this case, fortunately, the customer had made bolometer readings on all of the perf tiles. So I took the customer's bolometer readings, matched them against our bolometer reading, our simulated outputs, and came up with an average error of 6%. Nice. In other words, based on location of tile measured versus simulated, on average we saw a 6% error between simulation and predicted airflow. And we've defined the supply temperature. That was a boundary condition set by measurement at 55 degrees. And the IT loads for the racks were measured. So we put those in. So that means that we got a pretty solid model, Liz. Wouldn't you think? If we've got
I would say so. Yeah, very much so.
Yeah. So let me just review for some of you that may not be aware of these metrics. Magnus already has defined them a little bit. Let me just go back over them quickly. PUE is total facility energy over IT energy. The DCIE is the inverse of that. So what we're looking at here is total facility. That's everything. That's power, cooling, chillers, PDUs, transformers, everything. All the power, even the heat transfer through the walls would be in that numerator. And in the denominator is the IT equipment. So what this one says is, how well is my infrastructure doing when it comes to taking care of my IT equipment? How effectively is it cooling it? And that's what PUE is. 75% of the non-IT load in data centers is crack and chiller. So in that numerator we were just looking at before, it's really dominated by the compressor and the heat distribution or rejection system. The rest of it is really second order. UPSs, PDUs, switchgears. PDUs and UPSs can pull a little bit, but they're not dominant. They're really second order compared to the cracks and chillers. So if you did nothing more than look at the crack and chiller system or their heat rejection system as a way to improve the energy efficiency in your data center, you'd be taking a great step forward. And PUE and DCIE are really just inverses of one another. The range for them in terms of goodness for PUE is down around 1.2. Typically you see them around 1.8 or worse. You'll see some of these worse today. Good is around 1.4. Just ranges to keep in mind. DCIE is actually a percentage number where the 100% being excellent, 100% means that it's equivalent, that effectively there is no cooling energy required. The window's open, I suppose, and you're in Alaska. That would be DCIE of 100%. And we've seen some of those. Yahoo, Liz, if you've seen, has one of those, but they use free cooling, outside air.
Sure, sometimes a year, right.
Yeah.
That's why Sweden has a big business going now.
That's
up in one of their little towns. It's for data centers.
I think they're using seawater in that case.
Well, in some of them, yeah, but Yeah, just the cold temperatures. Yeah.
Now, as Magnus mentioned, we have also RTI that we use. RTI is a metric. I think, Magnus, you were the first one to use this, right? You defined these early on?
Yes.
So I like them because they give you a single way to look at a couple of different things in the data center. This one, RTI, is looking at delta T's or delta flow rates, depending upon how you want to look at it. It's either rack flow rate divided by air handler flow rate, or air handler delta T divided by rack delta T. You can look at it either way, or measure it either way. But at the end of the day, what you want is you want a balanced ratio of delta temperature across the racks compared to delta temperature across the cooling units. Vice versa, you want rack flow rates to be even with air handler flow rates. In other words, you only want to put the amount of air into the room that you need to cool the equipment. And the reason this is true is because heat transfer takes time. It's not instantaneous. And if you put the air too fast by a heat exchanger, it just doesn't have time to do the delta T. The heat transfer, if you remember, is equal to the mass flow rate times the density times delta T. It's the mass flow rate that really gives you the opportunity for the heat transfer to take place, the delta T to take place. And we saw in our base case already that the airflow is so high that the delta T across one of the cooling units is only 3 degrees. Now, the problem with DX-based units is you are, in many cases, until most recently, unable to put variable speed fans on those units at all. So they're either on or off, and they run at full tilt when they're on. And because there's not often good air management in the room, you have a very inefficient system because it doesn't get a good delta T on the return, and it's way off its design center. The other metrics we're going to be using today are RCI and RCI high and RCI low. These are really a measure of compliance with the ASHRAE guidelines. You can think of these as just, does it comply to the recommended standards for rack inlets? And the recommended range for rack inlets in Fahrenheit is 64.4 to 80.6. And the allowable is a little broader, 59 to 89.6. So that's the plot I was showing you. We've added 2 plots. An RCI, recommended and an allowable, that just show you whether or not any rack inlets, which is really what you're interested in, fit within the guidelines as specified. So the value is, if it's great, then you're near 100%, acceptable, 90 and 95%, poor, below 90%. So we're going to try to get them as close to 90% as we possibly can. And so that's how we optimize the data center. We look at RTI, try to get that close to 100%, and then we drive the other 2 parameters as well. Now, we'll see that as we drive one, it has an effect on the other. So these are techniques we use for optimization.
Hey, Paul.
Yes.
It's a good description. Maybe something to add is that by having a few metrics, the optimization process suddenly becoming very simple. We just try to get those metrics into the right territory, meaning close to 100%. We did not use these metrics, and just using printouts from the CFD modeling, this process could be very cumbersome.
That's a good point, because the thing about CFD is that there is so much data. It's data overload, and it's hard to consolidate it into something that is easy to digest. And so I think that's a very good point, that there's just so much information coming back from a CFD analysis. It's important to be able to filter it down into something that you can compare from one case to another case, and these are good metrics to do that.
So we need that data from the CFD. That's a foundation for using these metrics. If you don't measure it straight up, that's possible too. But also another effect of using metrics is that you can actually track them over time. If you have a monitoring system, if you do CFD modeling, you can track them after doing permutations of your design.
Correct.
And I think that's exactly what Paul is trying to show, that just tracking these metrics, you can see whether one design is better than another.
That's
and
correct.
that can be tracked very easily in a graph.
Yeah, that's correct.
That's right. That's right.
So, as we saw in our first base study, let me just review where we are, sort of where we started. We have a coefficient of performance of 1.19. It's not good at all. Remember, this should be at least 3 for a DX-based unit. The PUE is 2.4. Remember, ideally, you'd like 1.2. So it's off by a factor of 2. The RTI is 18%, which means I have tremendous amount of bypass airflow. The RCI high is 100% because certainly no rack is too hot. But the RCI low, and the way we represent it here is less than 0. This leaves confusion, so it's terrible. It's bad.
So bad we don't even want to tell you how bad it is.
That's right.
Right.
And the total facility power here we're predicting to be 175 kilowatts. Annual operating cost $122,000, 664, based on 8 cents per kilowatt hour, which was what the customer was paying. So, conclusions here is the cost to cool this data center are equal to or a little greater than the power to drive the equipment. It's a factor of 2. We're paying as much to cool it as we are to power it. That's terrible. That's terrible efficiency. RTI, 18%, way too much airflow. So, what we try to do now is reduce the airflow to match what the racks need. Start to bring the cracks down. The question becomes, can you start shutting cracks off and still be able to maintain a sufficiently smooth and conforming rack inlet temperature? So you may want to do a little cold air management or air supply management or hot air management, and then start to raise the supply temp, because raising supply temp is going to improve the coefficient of performance because it makes the return temps hotter. So in this case, we use curtains, simple curtains. Now, in this case, this is a drop ceiling. It has a ceiling return plenum. That's a very nice thing to do for air management. Very nice feature to have. So we increased the height of the cold curtains, added some hot air management curtains, and then take a look at those effects. So back to the point Magnus made, we can now use these metrics and make parametric variations of a design and track the metrics to see how we're doing and head towards optimization. So here's the first run, same model as before, and what we've done here, as you can see at the top, it says we've turned off 3 cracks. We've only got 1 left. Remember, we only need 10,000, so I can shut 3 of them right off. Flip the switch, see what happens. Now, you don't want to do that in your real live data center without first building a model and seeing what will happen. But before I did, I took the liberty of adding a little bit of containment. You'll see over here, Liz, that I added just a little bit of hot aisle containment. These racks were up against the wall. There was a grill right near it, so I put a curtain around it. Curtains are cheap. They're made of plastic. They have links at the top that drop in case of fire. You can usually get them by fire code. They're usually quite effective. I also, over here, the customer had already put a curtain on the end of this rack aisle between these 2 rack rows. So I just extended it up to the ceiling and put curtains on top of the racks themselves to make this a cold aisle. So there was a couple small things I did here. This isn't a lot of money, to be honest. I mean, these kind of curtains for this data center, probably a few $1,000s at the most. Quite simple to do. Let's take a look at our summary report and see what happened. And I'll go right down to the energy report. Well, look, the coefficient of performance moved up to 2.12. So the fact that I dropped out 3 crack units means that I got a much better coefficient of performance. Now, the reason I know what that number is measurements the customer made. The customer made measurements on the power being consumed by those crack units. I know what the current going into each one of them is, so I can figure out the POP pretty quickly with that data. PUE is 1.72. I'm down below 2. Things are looking good. RTI now, Magnus, is 72%, 72.8%. So we're getting there. the first thing I always do is go for RTI. Try to get the airflow set so that the amount being required by the racks is equal to the amount being delivered. If you can get RTI to 100%, make it exactly the same, you'll optimize the efficiency of the heat rejection system. But the trick is, just because you're blowing 10,000 CFM, Liz, right, it doesn't mean it's going to get to where you need it to go.
That's exactly right. That's exactly right. Doesn't mean it's going where it needs to go. So.
That's right. So that's why we need CFD.
That's why you need CFD. Exactly.
CFD tells you where it goes. And so here we see RCI high is 100 and RCI low is still less than 0 because we're cold. Now, let's go take a look at our rack inlets. And we'll look first at the ASHRAE recommended range, and we see we're still too cold here, Liz. The whole thing's too cold, but we see some indications that things are getting
some improvement.
Some improvement, yes. If we look at the full range of inlet temperatures, you'll see here that the contours are starting to develop because I've reduced my airflow. And it's always a little hotter at the top, right? So if we take a look at the cross-section of this room, things are going to be getting a little warmer here. So we're seeing now temperatures get upwards of 70 degrees in this room. But remember, we're blowing air at 55 degrees. It's very cold. And in the CoolSim, you can also look at these other plots, like look at the airflow coming from the tiles. So we look at the tile air, and you see it's coming up, and you can look at a lot of bypass still going on. Over here, Liz, it's kind of interesting. It's coming right up out of these tiles and right up into these returns. And now here, actually, what I did is I reduced some of the leakage through this cage. I was assuming we could do something like put a curtain right across the cage. It would help in this case on the hot air side. So we've done a little bit with curtains, not a whole lot, and things have improved quite dramatically. And we have a series of animations. We've left everything here that was here before with CoolSim, so there's quite a bit of information from for you to take a look at. But the two we've added, and here's the hot air returns here. The two we've added are related to the conformance of the RCI high and low. Okay. Now, what we did here, I took one more step in this model. I'm now down to one crack unit like I was before, but I've increased the supply temperature here 65 degrees, 265, by 10 degrees, 265 degrees Fahrenheit. And this is what we do. We first get the RTI in place, then we adjust airflow to try to make it even, then we begin to increase supply temp. And the reason we're increasing supply temp is because the higher the return temperature, the better opportunity I have for efficiency in the heat rejection system. And generally speaking, for every 1.8 degree Fahrenheit, we get about 3.5% efficiency improvement out of the heat rejection system. That's a good rule of thumb, holds fairly well across all kinds of heat rejection systems, whether they're DX units or chillers. The point simply is to get the return temps up. So let's go see how this worked out. First, we'll look at our summary report, and you see the coefficient of performance came up to 2.55. So we're improving still. Our PUE is down now to 1.63 compared before to being well up over 2. RTI 72%. RCI high and low now, Magnus, both 100%. We've got total facility power of 115 and a projected cost of $80,000 per year compared to 122 before. So if we take a look at our recommended values, you see now everything's green, which implies we have no racks either over and no racks under. This is, I guess, the Goldilocks test, right?
Yeah.
The porridge is neither, it's just right. It's neither too hot nor too cold.
Too cold.
Interesting, if we take a look at allowable here, it is also fine, of course. 59, we've got a broader range to operate in, so everything's fine there too. So that's our optimal case. Now, there were other cases that I studied when I did this work because, you don't shut 3 cracks off at once. I walked towards it. I went down one, went down another, and so on. And in the final analysis, I was actually able to use this unit over here on the wall, which is a a newer Stolz unit and has a variable speed drive. So you're able to actually get it a little tighter. But based on those runs, things look quite nice. And here I went one step further and put a little more containment in place. You see I put some curtains over here on the hot side in case the customer wanted to go there. It wasn't necessary, but we modeled that too. And the contours just looked a little bit better. So let's step back and look at what we've done on this data center. The initial case was $122,000 a year, RTI of 18%, RCI high 100, RCI low less than 0. Total facility power 175. In scenario 1, we simply switched off 3 cracks, and in scenario 2, we increased the supply temperature of that single crack. The most important factor there is the coefficient of performance going up, okay, to 2.5. So things improved. You want that number to get as high as you can. Remember, it is the ratio of the rejected heat compared to the amount of work. So as the amount of work declines to get that rejected heat, the number rises. No cooling at all, you've got a COP of infinity. In other words, no heat pump. You've got the window open.
Mm-hmm. Mm-hmm.
And down below, we've got RCI high and low at 100 with our RTI at 72%. Now, we could try, Liz, to drive that a little harder. We've got right now I left it at a supply airflow of 15,000. The racks only need 10.
Mm-hmm.
But as you know, you will get to a point where you start to hurt your RCI high. You'll start to get some racks that are falling out of compliance.
Mm-hmm. Mm-hmm. Mm-hmm.
So this is a pretty good job right here. Pretty good optimization. We've got the metrics all near 100, and bottom line savings looks like $42,000 a year on operational costs. The cost of curtains for that room, the work that I did to put those curtains in, would be far less than $10,000. So this would pay for itself right away on this data center alone. So that's
hey, Paul,
yeah, go ahead.
Yeah, just a comment there. You're driving these metrics to get as close as possible to a certain target. For RCI 100% and RTI might be 100% too. But it's always a cost associated with getting a really good optimization. And I think this process of optimizing that you're showing now is great, because the closer you want to get to your targets, the more it's going to cost you. You need to deploy more and more expensive solutions, so it gives you a pretty good feeling when to stop, because there are air management solutions that cost money investment, and maybe it's not worth it to get RCI from 98 to 99. Mm-hmm. That's the time to stop.
Right.
Mm-hmm. Right. That's right.
So,
very good point.
Let's take a look at our next data center. This one is a similar situation, only 1,000 square feet in this case. Supply plenum 1.6 feet. Number of crack units 4. This is a little heavier in terms of load, 100 kilowatts, roughly 104, 105. Flow rate through racks 16,700. Flow rates through vent tiles 28,000 CFM. Now this one was kind of interesting, Liz. Let me just pop over to this model and show it to you. This one is such a small room with such a small plenum, 1.58 feet, that these cracks were actually walking the fan curves. These things were you can't put, in this case, I think there were 15 each, or were they 10s? I guess they were 10s. So you can't put 40,000 CFM into a 1.5 foot floor and have it work right. So now the way I was able to tell that is that, again, they had taken a bolometer and made measurements on the floor tiles, and they weren't matching the factory specs on the floors.
Yeah, right.
Just way too much pressure. So again, I backed them off to 7,000 each to match what they were measuring in that room, and it was because too much pressure caused by way too much airflow. Now, what they were telling me in this particular room is the customer was very concerned, and again, you have people in these rooms. These are customers' equipment. So the customers are very sensitive about cooling, and they wanted to make sure they had enough. So they overdid it. 4 units in one room. But the irony is that it actually doesn't improve your reliability. It actually makes it worse, because what happens is these crack units run on and off and cycle up and down, and as a result, they wear out quicker. The best thing for any piece of machinery is to run it within its design specifications. Run it where they designed it to be run.
Right.
We always used to call this running off design center. If you run off the design center of any piece of equipment, you don't know what's going to happen. They didn't design it for that. So
that's right.
It'll fail.
The design point. Right.
Yes.
Exactly.
Now, in this case as well, the customer had begun to use a little bit of partitioning. These partitions aren't hard partitions. These are curtains. These are, I mean, in airflow, as you know, it doesn't take very much to separate hot and cold. I mean, a cardboard would do it if it were allowed. It's not allowed, of course, because of fire. But it doesn't take much. Mixing occurs when the air just circulates among itself.
Right.
It's not a conductive problem. It's a convective problem. And reducing the convective heat transfer through curtaining, containment of some kind, helps a great deal. So let's take a look at this one. This is our summary report here. And again, I'll just drop right down to the data center energy report. Coefficient of performance 1.82, just awful. PUE is also 1.82, not as bad as before, but still pretty bad. RTI 56%. That means it's got well more than twice as much as it needs of airflow. There's no racks that are too hot, so RCI again 100%. But RCI low is 0, less than 0. Again, just terrible. And the annual operating cost with 4 cracks on, we're estimating it to be $129,000 based on the total facility power times the cost of electricity, again, 8 cents. So there's nothing here that I can show you, Liz, that is going to surprise you. The racks are too cold, so they're blue under our specification here for recommended. The flow rate from the cracks, it's going to look like a tornado in here. So let's take a look at air from tiles, and here's our air from tiles. And I asked the customer, well, what's this like in here? Oh, it's like standing in a tornado.
A wind tunnel. We talked about
tunnel.
it as a wind tunnel.
Just way too much airflow.
Just coming right up and going right over those racks and back to those crack returns.
Yes. So this is a visual representation of the RTI number that is, 54%. And this is the visual for that, right? Here's the bypass airflow. Now, the bad news here, Liz, is it's hurting us twice. First, we have to pump it with a fan. And number two, the fan's putting a thermal load in the room, and I have to reject it.
Right.
So not only do I have to put energy into the fan to blow the air to begin with, but then I have to reject that heat caused by the fan in the room through the heat rejection device, and I'm hurting my heat rejection device by making it too cold on the returns. Again, here, if we take a look at our returns, I bet the delta T across our crack units is going to be awful. And there we have 11 degrees on one and 12 degrees on another. So just nowhere near where we need them to be. So what can we do here? Well, again, turn off the ones you don't need and put some separation in place to drive for optimization. So here what I did is just take 2. It doesn't really matter in this case which 2. I tried them both. But if we try to review too many cases here, then it gets a little confusing for viewers. So I tried these 2. I turned these 2 on and the ones on the sides off and went ahead and ran the model. Let's first look at the summary report. Summary report says, coefficient of performance went to 2.8. I'm getting near 3. That's good. 3 is average for DX-based units. PUE 1.47, not so bad. RTI 78%, not so bad. RCI high 100. I'm not too, I don't have any hot spots, but my RCI low is still too cold. It's less than 0 again. So if we take a look again at our ASHRAE recommended range on rack inlets, we see here, this is kind of an interesting plot, Liz. We're beginning to see right near the top a little bit of conformance.
Where it's always warmer. It's always warmer up at the top.
Right. So we're seeing that the top of the racks in certain areas conforms a little bit, And I bet if we click the allowable range, it will be a little greater. See, because allowable allows you to be a little colder
Yep.
Than the 59 degrees.
Mm-hmm.
So
Mm-hmm.
there you go. But still a lot of airflow in the room. If we take a look at the airflow from tiles, it's still recirculating a little bit, but just not nearly as bad as it was. So then what I did, same thing, drive up temperature. Let's see what happens when we go up 10 points. When we go up 10 degrees in temperature, we improve the efficiency by just about 20%. It's a good rule of thumb. It's about 19%. Good rule of thumb to remember. If you can move your supply temp up 10 degrees, you're going to get about 19% energy improvement out of the heat rejection system. And it shows up right in the coefficient of performance. So the coefficient of performance now 3.34. Nice. My PUE 1.29. That's pretty nice. 1.2 is excellent. RTI high 100%, RTI low 100%. I'm sorry, RCI high 100%, RCI low 100%, RTI in this case 78%. Annual operating cost $91,000. So here again, Magnus, I think we've gotten right to that balance point where, you know, RTI not quite 100, but right up there near 80, and the other two at 100.
And also, to add something else, Paul, yeah, I think there's a point where you have to stop the optimization because it's going to cost you too much in first cost.
Right.
Yeah, that was my point before.
Yep. And here, I really haven't done anything other than what the customer already did in terms of curtains. The curtains were already there, so there wasn't really much that needed to be done. We extended them a little bit to the wall. They already were across the top of the racks. And the customer in this case wanted to study the effect of a ceiling plenum return as well, and I did do that in a later run, but didn't present it here today.
I would also think, Paul, that maybe this seems to be a little bit shot in the dark how to do this optimization. But after a short while, I think you get a hang of it. I mean, I don't mean you now, but a user get a hang of it, how to do it, and he understands that certain parameter is going to give that kind of result on this set of parameters. So the optimization process is going to be much easier after times. Has that experience what happens when you're changing a feature in the data center.
That's correct.
That's so true.
And we do have ways, you know, of putting optimization routines in place, but it really needs the user in the loop to know what the degrees of freedom are. Can you put curtains in place? Can you move cracks around? That kind of thing. So if we take a look at the scenarios here, two of them that I presented on this second case, we improve the coefficient of performance from 1.82 to 3.34. We improve the RTI from 56% to 78%. The RCI high was always low, was always 100%. It was always fine, but the RCI low was below zero for both the base model and even the first scenario. But as we moved it up to 65 degrees, we got 100% on it. So all of them came into conformance, and that might even be able to go up a little higher. I didn't start to run it higher. I left it at 65. The coefficient of performance moved up. Savings went to 29% as a percentage of annual cost, all related to the cooling system. It costs a lot of money to run these machines, as it turns out. And as I mentioned, I did do one with a ceiling plenum in place, and that's this particular design here. They have a deep plenum up on top, and they wanted to see the effect of putting a plenum in place. Of course, hot aisle containment in this case, well, it's actually cold aisle containment with hot air return in the room. Only problem with this method, I tend to prefer this hot aisle containment, and I'll show you here why. If you slice this thing at 6 feet, it gets pretty warm in that room.
Yeah.
Yeah.
Makes people uncomfortable even though it works.
That's right. If you do cold aisle containment, which is what I did here, the servers are happy, but the humans are not.
Yeah.
Because you invite somebody into that data center and they're effectively walking into the hot aisle return. Hot aisle returns running near 100 degrees tends to make people a little nervous.
Yeah, right.
And then you have the combination of servers with very high delta T.
Yes.
That can really drive, especially if you have relatively high inlet temperatures to the servers, then you get exceptionally high temperatures on the return side.
Yeah.
Right, that's very, very true.
So that's it for our formal presentation today. It's about 10 minutes of. I wanted to leave enough time to open up and to have questions for the 3-4 of us here. In this case, we didn't spend a lot of money. We used curtains. They're flexible curtains. They're made of effectively plastic. They're fused at the top. They drop in the case of fire. They're not hard at all, hard surface. They're soft. They're quite effective. They're very cost efficient. I estimated that to do those 2 data centers with those curtains, $10,000 to $20,000 at the most. Projected savings here, $80,000 a year from doing what we recommended. Reduction of 30% of the total data center power on 2 small data centers. Now, they don't have 2. They have a lot more than 2. So the opportunity to go through their data centers and make these kinds of savings is a significant opportunity for somebody who differentiates themselves based on cost infrastructure. So what I'd like to do now is open it up and see if there are any questions. Jen, I'll turn it back over to you to host questions and see if there's anything here that people might want to discuss.
Sure. We have one question and we have a comment. So the first one is, I cannot tell what he's pointing to when he's trying to show stuff. So I'm not sure kind of what that is. I don't know if you'd want to be clearer whether or not you're looking at the equipment, the images. If you could kind of elaborate a little bit more on that, that would help us out a little bit. That way we can go back through some slides if we need to point out some components.
Well, let me just ask Liz or Jen, you both are in different locations than I am. Were you able to see it okay?
Yes, we can see your mouse.
Yeah, okay.
Yep.
It could be on the receiver's end. I don't know, Jen, about that one.
Okay. All right. I just wanted to feed that with you. Okay. Another question is, what is the difference between curtains and rigid containment partitions, both in modeling and in real life, in relation to how they affect the air?
There is none. I mean, my point is that rigid enclosures are no more effective than these enclosures that I'm using here, Baffles, with respect to containing air, because again, it's not conductive heat transfer I'm worried about. You don't need to worry about the insulative quality of the structure.
Right, right.
It's convective. It's all convective heat transfer. We don't even model conduction in this case. It's not important. It's insignificant compared to convective. So I know that a lot of people are, I know that the enclosure manufacturers are enthusiastic about selling hard enclosures because there's more money to be made in the sale of hard enclosures. But it's not necessary. It might be prettier, but it's not, from an engineering point of view, any better. Furthermore,
all right, and then, go ahead, Paul.
Well, furthermore, you can tear down these ones easier than you can a rigid enclosure. So, for change in the future, it's much more effective with the soft enclosure. Okay.
All right, this question is just kind of a follow-on regarding curtains. Brand or also fusible link, how do they drop? Heat from fire or electric current?
Either one. I've seen them both ways. The cheaper one is heat from fire, but they also sell a fusible link. And Jennifer, who are the suppliers of these? I've seen a couple different ones. Bendix supplies them, don't they?
Yeah, well, we're familiar with Simplex.
Yep, Simplex.
Yep, that's definitely one that always comes to my mind. I see them a lot. Yep.
Okay.
All right. How do you stop air from backflowing through the crack units when they're shut off?
Good question. Fair question. I've seen it done a couple of ways. Depends on the plenum pressure. If it's a large data center and the plenum pressure isn't that high, then you don't have to do anything. It'll pretty much stop itself. Because remember, there's not a lot of pressure in these plenums. There really is not. If, however, it is high, then what you'll want to do is use a louver. A louver that opens in one direction and is spring-loaded to shut in the other direction. They sit underneath the cracks. You run them, they're open. As soon as you shut the crack off, the spring shuts them. So I've seen those deployed. Pretty inexpensive.
All right. When will the new version of the software be available to update existing case studies and a total rebuild required?
Was that one question, or were there three in there?
one question, but
a couple modifiers.
A follow-on from that.
We are in beta test right now with a few, I'd say an alpha test really, on CoolSim 4, and that's looking quite good. I modeled all of this today with CoolSim 4. We're polishing a few of the ease of use features in it to make it better. We're optimizing it for speed right now to make it faster. So we are hoping to get it out in the next month or two, but it's clear that it is ready to go, and just a matter of getting some of these last few things in it, such as performance improvement, interactive performance improvement, so that the GUI is a little faster, things like that. But it is working. You saw here some new results from the new post sequence on it, and yeah, it will be compatible in the sense that if you built models in the past, you will be able to read them into this new CoolSim 4 and be able to begin processing right from there. So, yep, not much longer.
All right, and then to update an existing case study, is a total rebuild required?
No, it is not. What you can do is take your existing files from CoolSim 3, read them into CoolSim 4, change parameters, and make another run. Output is all the same, so you can view the output outside of the application as I was doing today.
All right. What was the rule of thumb with 10 degrees Fahrenheit and 19% savings?
The rule of thumb that is used is for every 1.8 degree Fahrenheit of cold air supply increase, the efficiency of the cooling system increases by 3.5 points. 3.5%. Yeah. 3.5% for every 1.8 degree Fahrenheit increase is the rule of thumb. Now, I have researched this pretty heavily and found that it is generally true for all heat rejection systems, whether it's chilled water or DX-based units, because they all use an evaporator, and the reason that the number is there has to do with the reduced lift associated with higher return temperatures. The higher return temperature, the less lift is required to increase the pressure and therefore the temperature to get that heat rejected into your sink, your outside heat sink. So it has to do with lift, and all of these systems work the same. They just have the evaporator in a different location. The DX unit exposes the evaporator to the data center. Chilled water-based system has the evaporator outside and uses a cold water loop between the evaporator and the data center itself.
All right, next question. What percentage savings do you get by adding variable frequency drives to crack fan motors? And what is the return on investment?
Yeah, we have done webinars on that, and I could do another one. It is dependent on the situation. So it's pretty hard to generalize, Liz, I think, about that, isn't it?
Yeah. It's hard to generalize, but what you'd have to do is just run a couple of models with different fan speeds, and see what the lowest one is that you can tolerate, and then recompute some of those energy parameters.
It can be quite significant, Jen, because the relationship between power to drive a fan and the flow rate coming out of it or the energy required to drive it is a cubic relationship. In other words, it's a ratio of the RPMs before and after cubed ends up being the difference in power. So it can be quite significant to let those fans come down. And I'm an advocate of variable speed fans. I think it's the right way to get the data center in balance whenever you can use them. And the cost can be modest. For a chilled water-based unit that is really what they call a CRAH, CRAH, or chilled water air handler is the acronym. You can retrofit those things for a few $1,000s a piece. So those can be quite cost effective with respect to changing. DX-based units, the older ones, you can't put variable speed fans on because the evaporators will freeze. So in some cases you are constrained. It does depend on the situation. If whoever asked that question would like to contact me, we can take a look at their specific situation and talk about it or give you more detail.
Maybe we can say, Paul, is that it's not unusual to see savings in the range of 70 to 80%. It's pretty incredible impact.
Mm-hmm. They can be very high. And I think, Magnus, you'll agree the reason for that impact is you slow the air down, you get a higher return temp, and you get better efficiency out of that unit.
Mm-hmm.
Yeah, this 70 to 80% is really just on the fan cost because of that cubicle, near cubicle relationship.
Right.
Another thing to point out is that if you cannot change the airflow rate, and if you cannot increase the supply air temperature, it doesn't matter what air management measures you implement in your data center. It's going to give you nothing.
Mm-hmm.
Mm-hmm.
The key is that you must be able to increase the supply temperature and or reduce the airflow rate.
Correct.
Right. Mm-hmm.
That's
Now,
very important.
it's interesting you said and or, because if you simply reduce your airflow rate, your return air temperature will actually go up and your efficiency will go up.
Mm-hmm. Mm-hmm.
Yep.
But you might not be able to do that. Yeah.
That's right. Yep. Okay. Any others, Jen?
Next. Oh yeah, we've got a few more. RCI low and high is a great metric, but I also know a lot of data centers have opportunities for savings due to improper humidity control. Magnus, do you have any comments regarding metrics for proper humidity control?
No, there is not established metric for that, but I think it's a good point. Maybe there is reason to develop a similar metric for that.
I'd like to also point out that we can predict humidity. Humidity is something that can be modeled. We do model it, not in CoolSim, but we do model it in CFD and understand how to model it.
Mm-hmm.
It is a capability we have not yet added to it, but certainly the Fluent solver that we use can model humidity. Liz, you have more experience with that than I, but not a problem to model it at some point.
No, that's for sure. Mm-hmm.
All right. What kind of sensors are used to collect the data to determine where to place the air curtains?
We don't use sensors to collect data to know where to put the air curtains. We just simply look at the flow patterns generated by the CFD, and you can tell where to put them.
Mm-hmm.
It's not
where
difficult.
The air's leaking around
That's
from
right.
the back. You know, you
Correct.
look and see where it's leaking from the returns and getting drawn back into the inlets.
So you run a CFD model based on the current configuration, and then inspect the output. Inspect the flow lines, the path lines of air, to see where they're going, and then try putting blocks in place or barriers in place, curtains in place, to prevent the air from going there, and then run another model and see what happens. So you can determine where to put them through trial and error using a tool like CoolSim.
All right, just getting back to the humidity, there was a couple of comments. One was there is a metric for humidity per ASHRAE 20 to 80%, stay on the low end. And then just modeling humidity would be great. Have some requests for the functionality. Okay, so getting back to some questions. Oh, it does look like another comment. Agreed. In tropical climates like Queensland, Australia, dew point control is a critical control metric. So that was just some feedback. Okay, a couple more questions. Is there value in damper actuators in the floor tiles?
Good question. This is one that comes up a lot, Magnus. This is the damper actuator floor tiles. The corollary is fan trays in your perforated tiles. What is your opinion? Let me just ask you, Magnus, what do you think of that stuff?
Well, I think it's a mixed bag. It depends on the configuration of the data. If there is a fundamental, I mean, if they have a capacity of delivering what that booster wants from the raised floor, fine, it's going to work. But otherwise, the risk is that you're actually stealing air from other areas of the data center.
So in a situation where you're supplying 10,000 CFM from the crack unit and your racks want 15,000, putting a fan tray in place isn't going to help.
Well, I guess you have to know, yeah, if you know where there's a need for air and you can see where there's not a need for air. I mean, it's a little bit of a hit or miss thing, knowing which ones to block. I mean, some people do this by putting obstructions in the plenum too to try and guide the air to where they want it. But it's a little bit of a hit or miss. So just putting in the dampers, may not, it'll close off the air in one place, but it may not particularly send it to where you need it. So yeah, you have to experiment with it a little.
The other thing about fan trays is they do introduce more heat load into the room. You don't get something for nothing. You put a fan in a room, and it's going to heat the room up. So it does introduce, although modest, it does introduce a heat load. The tiles that are dampered, not so bad. A little bit better idea there because apparently, effectively they're going to close when they're not needed. But it is a control system, and all control systems are subject to their own set of feedback control loop systems and where the sensors are and if the sensors are in the right place. And so proceed with caution, I think, Jen, would be our answer on that one. Yes, these things do work, but it is case dependent.
All right, we got 3 more. What is commonly accepted pressure for raised floor if control is based on that delta to P rather than supply or return temperature control?
And
You want to know what the pressure drop is across the floor?
No, they're looking for, the question I think was, what is the range? What is an acceptable pressure under the floor of a raised floor data center? Again, it's dependent on the configuration of the room, dependent upon the number of cracks. I don't know an accepted range. Do you, Magnus, an acceptable pressure or recommended pressure under the floor? Yeah, Magnus may have left us. He did have to leave at 4.
Yeah.
So I don't know, I guess, is the answer to that, Jen. I don't know. I tend to work in flow rates and delta T's and let the pressure settle itself out. The floor pressure is not that high in these data centers. The fans don't produce a whole lot of pressure. They can't. They're just not designed to do it. So I don't know what the appropriate, what a
an
rule of
absolute
thumb.
value. It's
Yeah.
really hard to say.
Really
with
hard
an
to do.
absolute value of pressure.
By the way, it varies across the floor, so it's not even uniform.
Sure.
Yeah. So I'm sorry.
We use and will plot the relative pressure, relative static pressure, but we don't, in general, provide the absolute pressure, which would be, relative to some value that was preset.
Yep.
So.
Okay. Next.
All right, and then just a couple more follow-ons, I guess, from that. Is that not limited by the downflow crack?
Well, yeah, I think it's kind of governed by the flow rate coming from the cracks, the volume of the plenum, and the square footage, the open area of the tiles, all contribute to, determining what the pressure is going to be in the plenum.
Yep.
Okay, and then just another comment that surely the cracks won't operate above a certain back pressure.
Oh, that's for sure. That's for sure. I mean, the cracks are made to run with a certain delta P across them, and the fans in those crack units are all well defined with a curve that is effectively, going to show you flow rate versus pressure drop across the fan. So there will be a point where the fan starts to what we say walk the curve, walk the fan curve, and not be able to supply any more airflow because the pressure on the downside of it is too high. Well understood. Fans know, the fan manufacturers all provide fan curves, and you can tell when you get into a situation like that based on the downstream pressure. But even in that case, the downstream pressure is not constant. It varies, of course, across the room, across the underfloor.
Mm-hmm.
So, and each fan is different. So it's, for example, EC fans are different than the traditional scroll fans they use. So it's difficult to generalize it, I guess, Jan. It is case dependent.
Okay. Has CoolSim looked at raising the inlet air model temperature above 65 degrees Fahrenheit, say 75 degrees Fahrenheit, and if so, what were the findings?
I didn't chase it too high in this case. The customer didn't want me to, but it's easy enough to do. You can just put a different delta T in and go have a look at it. I have seen them run as high as 70 degrees before and be fine. If you can get the airflow correct, you can run them right up to 70, 75 degrees. You have to then begin to worry a little bit about humidity because your humidity is going to rise too. So you have to, there's a balance point there. The other point here is that a lot of these IT servers are variable speed fans themselves now. So there's a balance point where you get to the inlet temperatures up around 70, I think the number is 73 degrees. Those fans will start to kick into high gear, and now you're kind of defeating the point or the purpose because you've got more fans, more energy, more, and you've, so there's an optimal point of supply temperature that's right around that 65 to 70 degree range and not much more. Okay.
All right, next question. Can a CFD model be run to analyze below floor plenum airflow characteristics? An example is return air is choked due to obstructions, heavy cable traffic.
Oh, sure. Obstructions can be placed, and we do it all the time, and we model everything in the underfloor and above floor. So if the user wants to replicate a obstruction under the floor, we allow you to put all kinds of things down there, all kinds of geometry. You can put cable trays down there, you can put pipes down there, you can put blocks down there, you can do whatever you want. We've had a few interesting ones where the underfloor is not uniform, right, Liz, where the underfloor has actually got a trough going through the center of it for some reason.
Right.
So we can model that too. And when we run a CFD simulation in Fluent, we mesh the underfloor and the room and the ceiling plenum too, all the volume. And we mesh it with very sophisticated techniques that are body-fitted in nature, body-fitted meshing. It's very advanced technology that allows you to very accurately predict airflow. Yep.
All right, our last question is, with return air temperature control, can raising the return air temperature work if you can't control supply temperature?
Well, yes, because if you slow down the flow rates, if you can slow the fans down on your crack units, the return air temps are going to be higher. So it will, remember the relationship is that heat transferred is mass flow rate times density times delta T. So you can hold supply temperature constant, reduce the mass flow rate, and your return temp is going to go up.
But you have to keep in mind the fact that the racks are going to be involved in this as well, because there's a delta T across the racks, and it depends upon what the flow rate coming from the cooling system is versus what the flow rate demand is. And if those two are closely matched, then whatever the delta T drop across the cooling system is going to have to match or come close to the delta T increase across the racks, across the equipment. So it all depends upon how the flow rates are varied as well.
And the geometry of the room, yes.
Yep.
But
all right, we did. Oh, you still going, Paul?
Well, no, but theoretically, yes. Theoretically, you can increase return temps without having to increase supply temps. Yep.
All right, we had another question come in. It's a general question. The presentation is focused on a traditional crack approach. What's the prevalence of direct cooling, liquid cooling of racks?
What's the prevalence? Not much. Not much. Now,
liquid cooling of racks?
Yes,
racks.
Liquid cooling of racks or liquid cooling of anything. We just don't see a lot of it. There was a prediction long ago that we're going to go back to liquid cooling and everything would have liquid cooling. I haven't seen it. And the reason we haven't seen it, and by the way, my background is in the computer business. I was in computer designed for many years for Hewlett-Packard, and it's economies, it's economics. It simply isn't cost effective to build a unique heat rejection system, liquid-cooled system for a computer when you can take off-the-shelf microprocessor-based parts from a PC and put it into a rack, and you're in the server business. It just isn't cost effective to do it from a supply point of view, from a computer manufacturer point of view. The cost gets to the point where it exceeds the cost of off-the-shelf components by so much that there are very few takers. The market for it is too small for anybody to be interested in it in a big way. I do see it pop up occasionally where small suppliers will come in and have unique mechanical systems for adding liquid heat exchangers inside the package, or back door, rear door heat exchangers. We see a little bit, but I don't see it becoming prevalent, and that, I think, was the question.
Well, that is all we have questions. You want to wrap up?
Sure. Final slide here. Thanks for coming, and we try to do this. I try to do it every other month if I can, and if you have a case you would like us to look at, let us know, and we'll model it and take a look at it and do some conclusions for you. We would like to be able to share, obviously, the case with the audience. It's not necessary that we reveal your company's name, although it would be nice. But instead of just coming up with cases that are theoretical, we like to work on real-world cases. And if you've got some measurements that we can validate the case with, it makes it much more realistic. So I would invite you to contact us if you have something you'd like to model, in case you're interested in this. Otherwise, our contact information is here, and on behalf of Liz and Jennifer, myself, and Magnus, who did tell us he was going to have to leave a little early, I'd like to thank you all for taking the time to attend today.